Hello everyone, welcome to my channel. So I've started offering specialized one-on-one classes in physics, chemistry and math EE for both SL and HL. So for the rates, the standard rate is $35 per hour. If you book like 5 or more classes, it'll be 30, and if you book 10 or more, it'll be 25. So these courses will be tailored to your needs. Whatever you want to learn, we can discuss in these classes. Please don't hesitate to reach out to me. You can contact me at this given email and yeah, to schedule your class. So with this, let's get started with this paper. Thank you. Hello everyone. So today we'll be solving paper 1 BSL of time zone 1 of the May 2025 exams. So let's get started with the first question. So a student is investigating the concentration, like effect of concentration on the rate of reaction between sodium thiosulfate and hydrochloric acid. Yeah, they have given you the reaction here. Since solid sulfur product is insoluble, the rate can be determined by measuring the time taken for the clear solution to turn off white or pale yellow until the X mark on the white tile below the flask can no longer be seen. So basically, we'll be like start like whenever the reactants are added, your timer starts, and when this cross mark below this conical flask disappears, we stop the timer. Right? So that's how you can measure the rate. Now, first, we have to determine the mass of sodium thiosulfate needed to make 500 centimeter cube of a 0.15 mole per dm cube solution. So, moles will be concentration times volume, correct? Concentration is 0.1500, volume is 500.0. Just dividing the volume with 1000 to convert it to decimeter cube. We'll get the answer as 0.07500. Okay, I'm maintaining four significant figures here. Yeah. And then mass will be moles times the molar mass. Yeah, moles is this. Molar mass we have to evaluate. So sodium thiosulfate is Na2S2O3. Yeah. So sodium is 23, to 2 times 23, sulfur is 32, and oxygen is 16 approximately. If I put it in a calculator, I'll get 11.85 grams, which is our final answer. Now we have to explain how to make this 0.15 mole per dm cube solution in a volumetric flask. Okay, so first we have to exactly measure 11.85 grams of sodium thiosulfate and transfer it to a volumetric flask. Then water has to be added until the 500 centimeter cube mark. And finally, the solution has to be shaken until all of the sodium thiosulfate gets dissolved and we get a clear homogeneous solution. Thiosulfate is dissolved and a clear is obtained. Done. That's it. Now to the next one. We have to suggest how we could make a 100 centimeter cube solution of 0.03 mole per dm cube sodium thiosulfate from the original 0.15 mole per dm cube. So first I need to know how much volume of this 0.15 mole per dm cube solution is required. For that we can use the dilution formula, which is C1V1 equals C2V2. So 0.15 times V1 equals 0.03 times V2. V2, we can take it as 100. If you take V2 as 100, V1 will come out in centimeter cube. So if I solve this, I'll get V1 as 20.00 centimeter cube. So I need 20 centimeter cube of the original solution. Yeah. Now if I try to write the steps, it will look like this. So 20 centimeter cube of the 0.15 mole per dm cubed solution has to be measured. As it's a small volume, we can use a pipette to measure it accurately. And this has to be transferred again to a 100 centimeter cube volumetric flask. After this, we have to add distilled water until it reaches the topmost mark, and then we just have to shake the solution so that it gets mixed properly. Until the total volume and has to be shaken um, such that everything gets mixed. Done. Next, the student recorded the following data, so they have given us a proper data table, right? The solutions of sodium thiosulfate were made as accurately as possible from solid sodium thiosulfate by weighing the appropriate mass with a balance that can measure to 100 of a gram rather than by dilution of a stock solution. So you're preparing it from you have solid sodium thiosulfate, you're mixing it with distilled water and preparing these solutions, which is obviously much more accurate. Yeah. Explain why percentage uncertainties of concentrations increase as the concentration decreases. Yeah, because your absolute value decreases. Thing is, your like if you check the errors will remain constant. Yeah. So like your absolute error or the error divided by the absolute value times 100 gives you the percentage error. And your error remains the same, but the absolute value becomes smaller. Then what happens? The percentage error increases. So that is the concept. Now, to write it, we can write it like this at lower concentrations. Mass of sodium thiosulfate is lower. Basically, the absolute value is lower. Hence, the percentage uncertainty will be higher. That's it, and that's probably it for a one marker. To the next part, we have to state one safety concern and one precaution. So for safety concerns, and I'll look at the reaction. SO2 gas is produced. SO2 is an acidic gas. It's highly corrosive, right? And it could be really harmful if someone accidentally inhales this gas. So yeah, that would be the safety concern. Concern would be SO2 gas is produced, which is highly corrosive and can harm the respiratory tract. Now, what's the precaution? How can we protect ourselves from this? We have to use the respirators. That's it. The respirator should be used. Yeah. Now, the next one, or the next question. A student was given a mixture to separate and collect individual components. Okay, the mixture contains sand, sodium chloride, salt, and iron fillings, Fe. Student observed that original mixture and made the following hypothesis. The iron would have the lowest percent by mass because it appeared to be present in the smallest quantity. That means the iron has had the smallest volume. That's what they meant here. Okay. Suggest a set of experimental steps required to obtain pure samples of each component of the mixture. Okay, so first we can use a magnet to separate out the iron fillings. A strong magnet can be used to remove the iron fillings. Then, so if I just move a magnet around this mixture, I would be able to remove the iron fillings done. Next, what we can do is we can add water to the remaining sand and salt solution. What happens? Clearly, sodium chloride will get dissolved in water, sand won't be. Then we can just use a filter paper to separate this for salt solution and sand. Then we can just dry sand, dry the sand to remove the water. Done, you got sand, and then we can boil up the water and we'll obtain the salt. Yeah. So next, water should be added. The remaining mixture. Okay. So NaCl dissolves in water, but sand doesn't. Yeah. Then this sand water solution can be filtered using a filter paper. Okay. So wet sand stained on the filter paper should be dried to obtain sand. Now, the salt water solution should be boiled to obtain NaCl. Done. So these are the steps we can use to separate these three substances. Now he has collected the following data. We have iron after separation, sand after separation, and salt after separation. You have to calculate the percentage composition of iron and sand. For iron, mass of iron is 2.17. Total mass of the mixture is 5.62. Times 100, this will give you 38.6%. And then for sand, it's 1.98 divided by 5.62 times 100, which gives you 35.2%. These are your percentage compositions of iron and sand. Next, the percentages in B add up to more than 100. Suggest a reason that would explain these results and how to reduce or eliminate this issue. So it can be more than 100. only when we have overestimated something. Yeah. And that is possible in case of either sand or salt, because in both cases you have mixed them with water. So one guess would be that the sand, right? The wet sand had not dried properly. There is still water in this wet sand. As a result, we have accidentally overestimated the sand mass, right? So that gave you a bigger percentage, and hence the total percentage composition came out to be bigger than 100. It could be possible. So for the reason, and write it like this: water may not have been completely removed from sand. How can we reduce this? So we should heat the sand or dry the sand until it attains a constant mass. Now, the results did not support the original hypothesis. Okay? The original hypothesis said that the percentage composition of iron should be the lowest. Yeah, this is the hypothesis again. Iron would have the lowest percent by mass, but if you check here, iron has the highest percentage by mass. Okay, so why is this hypothesis wrong? Because iron has the highest density, even if iron has the smallest volume. This small volume will have a higher mass as compared to salt or sand. This is why the hypothesis is wrong. So you can write it like this. Iron has the highest density in this mixture. So even if it appeared to have the smallest volume, it had the highest mass. That's it. The next one. A colorimetry experiment was conducted on a series of solutions of copper to sulfate. The absorbance versus concentration data was graphed. We have to draw a line of best fit extrapolating beyond the given data. Okay, fine. So when concentration is zero, absorbance is zero. So we have to start from the origin. Okay. So I'll just draw a line and then I can adjust this line a little bit. And during the exam, you have to draw this line using a ruler. Okay. So the line should pass through the origin, and you have to make sure that this line basically touches all of these points at like somewhere it should be inside. Yeah, it should not miss any point completely. So that is the line of best fit. I can maybe remove this initial part. No, it's okay. Let it be. Now we have to state the mathematical relationship between absorbance and concentration. Absorbance and concentration gives you a straight line. So you can say they are directly proportional, or you can say A is equal to Kc, something like that. So is directly proportional to concentration. To say A is equal to Kc, where A is the absorbance, K is the concentration. I mean, C is the concentration, K is the slope of the line, which is a constant. We have to deduce the equation that relates absorbance to concentration, including the value of the constant. So equation will look like this. A equals Kc. Yeah, now we just need 1 point. So you can take this point here. So A is equal to 0.2 when C is equal to 0.1. If we plug these two here, 0.2 equals K times 0.1, we get K as 2. So finally the equation becomes A equals 2C. Fine. Next, estimates the absorbance value of 0.6 mole per dm cubed CuSO4. This is the line, so the concentration is 0.6. So from here, I'll just draw a straight line upwards. So might have to make the line a little bit thinner. Yeah, done. Now draw a straight line to the y-axis. Now, if you check this carefully, right, it's below the halfway mark. So this is 1.3. Um, yeah, this is 1.2. Oh, this is, no, wait, this is not 1.3. I have 1.22, 24, 26, 28. No, no, it is 1.28, I believe. 32, 36, yeah, 1.28. So this midline is 1.24. So it's in between 1.28 and 1.24. It's around the midpoint. Yeah. So it should be 1.25. Yeah. So from the graph, I'll just check something again. 0.2. Yeah. Okay, fine. Your absorbance would be 1.25. Done. So that's all about this paper. I'll shortly be posting the other paper 1B solutions. Thank you so much. Bye.